up in Minnesota. I went to in St. Paul. I went to St. Thomas Military Academy and also the College of St. Thomas. So I lived in Minnesota several years, and then from here went on to Michigan State University, and then I worked for the DuPont Company in Delaware for several years, and I now reside in Friendsville, Tennessee, home of the recent tornadoes.
Yeah.
We've had a few of those.
Yeah.
Okay, today we're going to talk about some of the characteristics of thermoplastic, or you might know it as plastic joints. So primarily we're going to be talking about the two most common types of plastics that are used for piping applications. That would be PVC and polyethylene, or you may know it as HDPE. In the first half of the presentation, I'm going to talk about correlating plastic pipe RCP. RCP stands for Rapid Crack Propagation. Field failures with the calculated critical pressure for water pipe applications. And the first thing we're going to do is to talk about what is rapid crack propagation. These are long-running cracks that we'll be discussing. Then we're going to look at some of the test methods that have been used to determine the resistance to rapid crack propagation. We'll look at the data from these test methods, specifically for polyethylene and for PVC. And then we're going to look at some actual case studies, some field failures that have occurred in plastic pipe, and how the actual field failures compare with the laboratory data, and then make some concluding remarks for this part of the presentation. The second part of the presentation will deal with butt fusion data that we have. So, what is rapid crack propagation? Rapid crack propagation is a very fast fracture, 1,800 feet per second. Now, how fast is 1,800 feet per second? Imagine that you're a football star. Adrian Peterson, he's a local boy, right? We'd all like to be Adrian Peterson. Imagine you're Adrian Peterson standing on the goal line, and you run all the way to the other end of the goal line, and back, and down, and back, and down, and back, in 1 second. You can do that, right?
Every day.
Young fellow?
Every day.
That's pretty fast. So when we're talking about these long-running cracks, 1,000 feet, 1,500 feet long, they actually travel that distance in less than 1 second. So it's a very, very fast fracture. It's referred to as a catastrophic failure of the pipeline, typically related with what's sometimes called an explosion. These cracks can travel very long distances, as you'll see in some of the examples I'll show, over 1,000 feet. And whether it's plastic pipe, these type of failures also occur in metal pipe. In fact, they originally occurred in metal pipe, and all the original research that was done was on metal pipe, and these were the test methods that were then used for plastic pipe. These cracks usually initiate at some kind of a defect. Might be at a butt fusion, could be during an impact. Sometimes they occur during a leak pressure test. Sometimes they occur during a tapping operation. But in all cases, you have to have a pressurized system, and you have to have enough energy in the system to drive the crack faster than the energy is released. It's important to know that RCP, or rapid crack propagation, it's an engineering property of the material itself. It's different for different types of metals, it's different for different types of plastics. And various piping materials will behave differently in an RCP event. For some ductile materials, like polyethylene, the crack basically is arrested as soon as it occurs. RCP, or rapid crack propagation, is not very common in polyethylene because of the inherent toughness of the material. For other materials that are more brittle, the pipe can shatter during an RCP event, or it can travel long distances, over 1,000 feet. Let's take a look at some of these plastics. One is polyethylene, and a number of people use polyethylene for a number of different piping applications. Polyethylene is a semi-crystalline material. It's well above its glass transition temperature. It's a ductile material. It's not a glassy or brittle material. And because of that, it's very resistant to rapid crack propagation. There have been some RCP failures. There's probably been about 2 or 3 worldwide that have occurred over the history of polyethylene. The polyethylene has been used for well over 50 years. There have been no RCP failures in the past 20 years in polyethylene. And its failure rate as far as RCP is concerned is very, very low. In most European countries, polyethylene is used a lot more for water application than it is in the United States. In typical European countries, about 50% to 90% of all the pipe used in water applications is polyethylene, same type of polyethylene that we use here. In the United States and also in Canada, anybody know the percentage, roughly? 3. About 3% of all the pipe that's used for water applications is polyethylene. If we look at PVC pipe, PVC is a very common plastic pipe material. It's about 7 billion pounds a year. It's used in a variety of applications. As far as a type of plastic, it's known as an amorphous plastic, and it's below its glass transition temperature. So it's in a glassy or brittle state. In the U.S., there have been a few RCP failures that have occurred in bell and spigot joints. When these failures occur, the crack generally travels as far as the bell and spigot joint, and then it stops. There's a discontinuity between the bell and the spigot, and that discontinuity stops or arrests the crack. Failure rate is about 0.02 failures per million feet. And as I said, they only travel a few feet and then arrest at the joint. Recently, at least 20 RCP failures have occurred in PVC pipe when it's joined by the butt fusion method. Now, the butt fusion method is a very good joining method, but an RCP crack will travel through a butt fusion. That failure rate is about 5 RCP events per 1,000,000 feet. And these cracks travel for hundreds, over 1,000 feet through the butt fusion joints, as you'll see. These are some of the long-running cracks that have occurred in butt-fused PVC pipe. They've occurred in various parts of the country. Some of the places local to here would be in Greencastle, Indiana, Des Moines, Iowa, just south of here, in Springfield, Illinois, Green Bay, Wisconsin, just a little bit west of here. If you're a Packer fan, you obviously know where that is. There wouldn't be too many Packer fans around here, right? And in Evansville. It occurs in various pipe sizes, ranging from 8-inch to 36-inch, various DRs ranging from 18 to 32. And as you can see, they travel generally several hundred feet, a number of them over 1,000 feet. This one went 1,100 feet in Florida. This one went 1,600 feet, another 1,100 feet in Iowa, 1,200 feet, 900 feet. This one in California went 2,000 feet. And again, all of these were joined by the butt fusion method. This is a 30-inch DR25 PVC pipe that experienced a rapid crack propagation failure. It went 1,100 feet. 1,100 feet, that means the entire pipeline fractured in less than 1 second. Yes, sir?
Okay, on the bottom there it says due to
contractor error.
What, just the bedding of the pipe or?
Something that the contractor did during the leak pressure test. Maybe they didn't use the right test cap. Maybe they didn't do something proper. So generally it's something that the contractor does incorrectly that results in the crack initiating. Once it initiates, then it propagates. Okay, but you have to have something to initiate it. Okay. So we need to, as water engineers, we need to design against RCP. No matter what the type of material, whether it's plastic pipe or metal pipe, we need to design against RCP from occurring. RCP no longer occurs in polyethylene. It occurs in belt spigot, but it only travels as far as the next joint. So it might go 5 feet, 10 feet, so it's not as big of an issue. It's not the entire pipeline that's being destroyed. Since long-running cracks occur in butt-fused PVC pipe, we simply need to understand this phenomenon so we can design against it. We're not saying don't use plastic pipe. We're not saying don't use PVC. We're not saying don't use butt fusion. We just need to learn how to design to prevent it from occurring. So let's look at some of the test methods that are used to determine resistance to these long-running cracks or rapid crack propagation. Internationally, there are 2 test methods. One is known as the full-scale test. You basically have a 50-foot section of plastic pipe, a 100-foot section of metal pipe to carry the reservoir. You have to do it at least 15 or 10, 15 times in order to determine your critical pressure. It's a very, very expensive, typically about $300,000 or $400,000 to determine your critical pressure. So it's a very expensive test method. A few years ago, Dr. Pat Liebers at Imperial College in the UK developed what he called the small-scale steady state, or the S4 test. Both of these are ISO tests, they're international test methods. This uses much smaller pipe samples that can be done in a laboratory, and once we get the data, it can be correlated to the full-scale test. This is what an S4 test looks like. This is the rig, and these are baffles that are in the middle. Because of these baffles, that's why, and it has to do with the wave speed, that's why we need to have a correlation equation to correlate the data from the S4 test with the full-scale test, which is the real answer. This is what I mean by the critical pressure. This is simply a plot of the length of the crack versus pressure. At lower pressures, the crack arrests. It doesn't go a very long distance at all. At higher pressures, the crack propagates. It goes to the end of the pipe. In this case, this would be a 9-foot section of pipe, and it goes all the way to the end of the pipe. It propagates to the end. Okay. The units here, if you're not familiar, these are in a bar. We all know what a bar is, right? That's where we go to have libations. No, a bar is it's an international unit for pressure. 1 bar is 15 psig. But typically, the data are always obtained in bars when we do RCP testing. So this is the critical pressure. From an engineering point of view, it's important to know what the critical pressure is. Why? Well, if we're above the critical pressure, if the pressure is higher than the critical pressure, it's possible for RCP to occur. If we're at pressures below the critical pressure, RCP will not occur. So from an engineering point of view, from a design point of view, we want to be below the critical pressure. Okay, so let's take a look at the S4 test and how does that correlate with the full-scale test. This term here, P sub C is the critical pressure, and Fs stands for full scale. So P sub C, Fs stands for the full-scale critical pressure. That is equal to whatever critical pressure we obtain in the S4 test, we multiply that number by 3.6, and we add 2.6 bar. That is how we get to the full-scale pressure from the S4 critical pressure. And this equation that we'll use, it's independent of pipe size. We can use it on various pipe sizes, we can use it on various materials, and we can use it with various fluids like water, air, etc. Alright, so now let's take a look at some actual laboratory data for the 2 commonly used materials, plastic materials, polyethylene and PVC. This is a plot of the critical pressure as a function of the percent of air. These are data from Dr. Pat Liebers. Most of the time, this S4 test is done in 100% air. That's the easiest way to do test. And if you're looking at gas pipe, for example, then that would correlate. However, we also want to look at this for water pipe, when we have 100% water. We can also do the test in 100% water. And as we can see, when there's zero air or 100% water, we get a much higher critical pressure. Remember, the higher the critical pressure, the more resistant it is to these long-running cracks. As the air increases, the critical pressure decreases, and it starts leveling off. This is important because what it means is that we can do the test in 100% air, and it's the same critical pressure as a situation where we have 20% air and 80% water, which is a situation where you might have entrapped air. We know that you're not supposed to have air in your water, but there are cases where there is entrapped air, and many times in these failures that have occurred, it has been reported that there is entrapped air in the water, and that helped to cause the long-running crack. So this is the critical pressure that we'll use, in this case 3 bar. This is the correlation equation that we talked about. The full-scale critical pressure is 3.6 times 3 bar plus 2.6, which is 13 bar. Multiplying that by 15, we get to about 195 psig. That's the critical pressure for this DR11 polyethylene pipe. So, what do we do with that? Now we decide how does that compare to the actual operating pressure, or the pressure rating. The pressure rating is actually obtained 2 ways. One is the standard pressure rating equation. That's the equation you'll see in the ASTM standards, the AWA standards, as based on the HDB or the hydrostatic design basis. The other way to determine the pressure rating is to base it on the critical pressure, and to make sure that the critical pressure is greater than 1.5 times the pressure rating. Why 1.5 times? Because typically that's where you do your leak test. That's the pressure for your leak testing. 1.5 times your pressure rating, or sometimes 1.5 times your operating pressure. So we're going to look at the pressure rating obtained by the pressure rating equation and by the critical pressure. Taking a look at this example, this was DR11 polyethylene that was tested. According to the pressure equation, it would have a pressure rating of 125 psig. Looking at its full-scale critical pressure and dividing by 1.5, it would have a pressure rating of 130. We used the lower of the 2 values to be more conservative. In this case, the pressure rating, the standard pressure rating from the HDB is lower, so that would be the pressure rating for the pipe. Some of you have heard of the new PE 4710 materials. These are the materials that can use the higher design factor. In this case, DR11 with a 0.63 design factor can be used up to 200 psig. Now we're getting to some higher pressures with polyethylene. But how does that compare to the critical pressure? Because again, we don't want to be close to the critical pressure. The critical pressure for this material is 664 psig. That's about 3 times the pressure rating. Dividing this by 1.5, we get to 440. The pressure rating calculated of 200 is way below the critical pressure, way below the pressure rating limited by RCP. RCP is not an issue with the new polyethylene materials. Yes, sir?
Is the safety factor 1.6? It's not
1.5.
up top on the 0.63?
0.63. Oh, that's the design factor.
Right. So if you did the safety factor on that pipe is what?
That's the design factor.
Yeah. But what is the safety factor on that pipe?
Well, the term that's used in the AWWA and ASTM standard is the design factor, and the design factor times the HDB, that's known as your hydrostatic design stress.
Right, and that would be...
Right, and actually that's where the 10 comes from, the 1600 psi times the design factor of 0.63, that's 1000 psi, and that's actually where the 10 is. The 10 is your hydrostatic design stress.
So the safety factor on that pipe is a 2.0, is that what you're saying?
I'm not sure what you mean by the term safety factor.
The standard safety factor on pipes is designed as 2.0.
You're talking about a design factor of 0.5. For example, the previous example had a 0.5 design factor. You could call that a safety factor then of 2.0. Is that what you mean?
Sure.
Sure, okay, yes. This is a design factor of 0.63, so it would be a safety factor of about 1.7, whatever it turns out to be. Right, right.
Okay.
And this was done with these PE materials simply because of the much higher resistance to slow crack growth, which is how these materials fail in service. So that's what justifies the higher design factor. Actually, this design factor of using 0.63 as the design factor, if you want to call it a safety factor, ends up with a pressure rating of 200 psig. But this is still conservative. If we look at the ISO method of pressure rating and their safety factor that they use, DR11 would be operated at 232 psig. So even with the new higher design factor, we're still conservative as to what I would call the pressure capability of the pipe. And this material is used internationally with this kind of a pressure rating. Okay, let's take a look now at PVC. This is the data again from Dr. Pat Lieber's critical pressure as a function of the percent air volume. And we can see that in 100% water, we get the highest critical pressure, just like with polyethylene. And as we increase the air volume, the critical pressure decreases. And we get to about 10% air in water, it starts to level off. And that critical pressure is 1.6 bar. Now, if we take that exact same equation and plug in 1.6 bar for this DR19 PVC pipe, we get a critical pressure of 121 psig, or a critical stress of 1100 psi. If we look at the pressure rating equation, it's 4,000 psi, the design factor of 0.5, or safety factor, if you will, of 2 to 1. That pressure rating is 222 psig. With the full-scale critical pressure of 121 psig, dividing it by 1.5, that indicates a pressure rating of 80 psig. So if we're going to design against RCP from occurring, the pressure rating would have to be decreased from 222 down to 80 psig. That equation, or this critical pressure that we just calculated, is based on laboratory data and an imperial equation, the correlation equation. How does that correlate with actual field performance, actual field data? Well, let's take a look. And we'll do that by looking at an actual case study. Case study we'll look at is some actual field experience a little bit south of here in Springfield, Illinois. They used butt-fused 18-inch DR25 PVC pipe and was held at a pressure of 60 psig for a few days. They had no problems. Recall that for PVC pipe, based on the Dr. Lieber's S4 critical pressure data and the ISO correlation equation, the full-scale critical pressure for DR25 pipe would be 91 psig. Again, that's based on the stress. Once we know the stress, we can determine the pressure for any DR, dimension ratio. Okay? So what that says from the equation is the critical pressure is 91 psig. That means if the internal pressure is less than 91, RCP will not occur. What that says is if the pressure is over 91, it's possible for RCP to occur. What actually happened is that when the pressure for this 18-inch DR25 pipe was increased for the leak pressure test, a crack initiated when the pressure reached 100 psig, and it propagated 850 feet going through 21 joints. This is the actual value where the pressure where RCP occurred. That's called propagation when it goes 850 feet. We know the critical pressure, therefore needs to be lower than that. The calculated value is 91, so there's very good agreement between what actually happened in the field and the calculated value of 91. When it got just above 91 psig, the crack ran 850 feet. So if we do the same analysis for this DR25 pipe, the pressure rating, according to the pressure rating equation with the standard 0.5 design factor or 2-to-1 safety factor, is a pressure rating of 165 psig. With a calculated critical pressure of 91 psig, the pressure rating would be 60 pounds. Again, considerably lower than the pressure rating calculated from the full capability based on the HDB. But again, that's what the pressure rating needs to be if we're going to prevent RCP from occurring. Okay, let's see if we can make some concluding remarks. These are some of the failure rates that we discussed with the PE 4710 materials based on the critical pressure that's been determined 3 times the pressure rating. RCP will never occur in a PE 4710 material. For the earlier generation polyethylenes, we estimate the failure rate is about 0.0005, or very low failure rate. For PVC joined by bell and spigot, it's a little bit higher, 0.02 failures per million feet. But again, here the crack only travels a few feet. And for PVC joined by butt fusion, the failure rate over the last few years has been about 5 failures per million feet of pipe. So this summarizes then what we learned about the pressure rating, and the pressure rating determined by the full scale, or really limited by the full scale, the pressure rating by the HDB. For the DR19 pipe that Dr. Liebers examined, the full-scale critical pressure is 121. That means the leak test pressure should be less than that, or let's say 120. If the leak test pressure is 120, then the pressure rating is 82. Excuse me, is 80. Considerably less than the pressure rating calculated by the HDB. For DR25 pipe, the calculated full-scale critical pressure is 91. That should be greater than the leak test pressure. So if we limit the leak test pressure to 90, the pressure rating is 60. Again, considerably less than the pressure rating calculated by the HDB. In the case of polyethylene, the critical pressure is 664. We don't leak test pressure this high, but it could have a leak test pressure as high as 660. With a pressure rating of 200 psig, the actual pressure test is 300 psig. That's where 200-pound polyethylene would be leak pressure tested. But again, the actual pressure rating and the leak test pressure is considerably lower than the critical pressure. So how do we prevent rapid crack propagation in polyethylene? The best way to design against a rapid crack propagation occurrence in PE is to select a material that has very high resistance. Most of the materials, polyethylene materials, do have very high resistance to RCP. The critical pressure is generally higher than 1.5 times the leak test pressure. As long as your critical pressure is higher than 1.5 times the leak test pressure, RCP will not occur. With the 4710 materials, it's so high it will never occur. How do we prevent rapid crack propagation in butt-fused PVC pipe? The critical pressure for butt-fused PVC pipe is only half of its pressure rating based on the HDB calculation. This is why there have been so many RCP failures. I had a table earlier showing you about 20 of them. That's just the ones that I'm currently aware of. The key point is that the full-scale critical pressure needs to be greater than the leak test pressure, which is 1.5 times the operating pressure. If it's not, then we need to lower the pressure rate as a way of preventing RCP. Another way would be to, if you need higher pressure than what that calculates to, you need to use a thicker wall pipe or a lower DR number. So if you're using DR25, you might need to use DR18 or DR11 or whatever. Now this, using a thicker wall pipe, is exactly in agreement with Dr. Lieber's paper, where he basically states, when he's talking about wave speeds, the values correspond to a minimum DR13 for PVC and DR19 for PE80. That's the type of polyethylene he tested. Although such high DRs are rarely seen in PE80, almost all PVC pipe is thin-walled, at least higher than DR19, and as such is capable of sustaining RCP, and notice, in 100% pressurized water. So even in 100% water, it's possible to get RCP failures in PVC pipe, and that's what Dr. Lieber's observed. So, in summary, to design to prevent rapid crack propagation from occurring, to prevent these long-running cracks due to RCP and PVC pipe, the water design engineer should lower the pressure rating of the pipe such that the pressure rating is less than the full-scale critical pressure divided by 1.5, or use a thicker wall pipe, DR13 pipe or lower. To prevent long-running cracks due to RCP in polyethylene pipe, the water design engineer should use DR29 pipe or lower, or use a PE4710 material, and it'll never occur. Okay, let's now, we do it on time. Okay. Let's now take a look at some of the characteristics of butt fusion joints in plastic pipe that's used in water applications. We're going to have some background information, look at some laboratory results, look at some high-speed laboratory results, and look at also at some field experience for butt fusion and compare the two. Let's start first with just butt fusion in general. Butt fusion is one of the most common methods of joining thermoplastic pipe. It's used in polyethylene, now in PVC, it's used for polyamide, it's used a number of the fluoropolymers, so a number of thermoplastic materials are joined by this butt fusion method. And butt fusions are used because they provide a leak-free system. For example, in the gas industry, it's very common around the world, literally, to use butt fusion. Because butt fusion is a very good joining method. And obviously in a gas system, you want to have a leak-free system. And that's why butt fusion joints are very commonly used in the gas system. They're also commonly used in the water system. Butt fusion procedures were developed for polyethylene well over 50 years ago. So there's a lot of experience in butt fusion joining for polyethylene. PVC butt fusion procedures were recently developed as discussed in a 2003 paper by Mr. David Woods and Mr. Tom Marty. This is when they first developed the butt fusion joining procedure and talked about it for PVC pipe, which I thought was a very novel idea. In our research study, a third-party laboratory was supplied with polyethylene and PVC properly made butt fusion joints and the corresponding control pipe samples. It's always important when you want to look at joint integrity to take whatever the joint is and compare it to the parent material. We looked at standard ASTM test methods, we looked at the bead appearance, and looked at these test methods to determine the integrity of the joint. And what we're going to do now is to summarize the program that was just completed to assess the butt fusion integrity for polyethylene and PVC butt fusion joints using these test methods. So these are going to be the results of the standard laboratory tests that were used in this particular program. Just to give you an idea, this is polyethylene, and this is what a typical butt fusion bead looks like in polyethylene. This is what the butt fusion bead looks like in PVC. So that's just to give you an idea of what the beads look like in polyethylene and in PVC. The first test that was done is called the bent strap test. Basically, this is a test where you take a strap. The strap itself is about a minimum of an inch wide, several inches long, and you can see the butt fusion is in the middle. You then take the strap and you bend it. All of the polyethylene fusion bent strap test passed the requirements for a good butt fusion joint. All of the PVC specimens failed the requirements for a good butt fusion joint. The butt fusion failures in the bent strap occurred by brittle fracture of the PVC material adjacent to the fusion interface. So they did not pass that particular test method. Another test method that was used is what's called the tensile test. This is done in accordance with ASTM D638, where you take a tensile bar, and it has a machined area to give you a land area, and then you pull it at a slow speed. There's two types of tests we're going to look at. The tensile test, where it's pulled at a slow rate, and then a tensile impact test, which is a faster one. And there's a couple of tensile impact tests that we'll talk about. As far as the tensile test is concerned, these are some of the terms we're going to use. This is what's called a stress-strain curve, very typical for any type of plastic material. The stress is the load, and the strain is the deflection or elongation that you have. This is what's known as the yield point in the stress-strain curve. So this is the tensile strength at yield, and which is this value, and this is the elongation at yield. This is where the sample breaks during the test. So this is the tensile strength at break, and this is the elongation at break. And then the area under this curve is known as the energy to break. Okay? So looking at the tensile test results in polyethylene, we looked at the stress at yield, the elongation at yield, the stress at break, the elongation at break, and then the overall energy to break. And for all of these, you can see it's either just under or just over 100% when compared to the same exact test done on the same exact type of specimen taken from the control pipe. The only difference is the butt fusion had the butt fusion in the middle, the control pipe has no butt fusion, it's just the same parent material without the butt fusion. These are the results of laboratory testing for PVC. The stress at break is 85%. So as far as the stress is concerned, the tensile strength at break, it's fairly high. But if we look at the elongation at break, it was only 3% of the control pipe. If we look at the energy to break, which is the area under the curve, it was only about 2.4%. And they note here that these are the values of break. They could not measure the yield values because the joints broke before obtaining the yield. These are results of tensile impact testing. The tensile impact testing is similar, but it's done at a faster rate. It's using an anvil, and you like impacting. So one is pulling, the other one is impacting. And again, we want to look at the energy to break and compare it to control. These are the energy to break values for the butt fusion joint and the control pipe. In the case of polyethylene, it's 70%. This is a very common test method. In fact, this is probably the best test method to use for butt fusion joint integrity. The typical industry guideline is between 50 to 100% is a good butt fusion. Between 25 to 50% is a marginal fusion, and below 25% is a bad butt fusion. So 70% is a good value. These are the actual tensile impact specimens after testing, and these are the butt fusion on the right, and you can see in every single case you see elongation, you see ductal tearing, typically just one side or the other of the butt fusion. This is an indication of a properly made butt fusion when you see this ductal elongation. In the case of the PVC butt fusions, for the joint was 26.6 kilojoules per meter squared. For the control pipe, about 5.9, and basically it was about 5% compared to the control pipe. These are the specimens for the butt fusion on the right, and you can see there's almost no ductility. There's basically a brittle breakage right at the butt fusion. What we then did was to compare these results to a published report where tensile testing was done, but in this case it was high-speed tensile impact. This is a newer test method that was developed by McElroy Manufacturing and has been used for polyethylene for a number of years. This testing was also done by another laboratory on PVC butt fusion joints. Our tensile impact data, we felt for the PVC butt fusions agreed quite well with this report that is in the literature, fusible C900-905 PVC test data and pressure properties for a fusion joint. For this particular report, the laboratory used a McElroy-McSnapper high-speed tensile impact test in accordance with the ASTM test method. The ASTM test method is the standard test method for laboratory testing. It says here of butt fusions, joining. They use the same test method for PVC, which is perfectly fine. There's nothing wrong with that at all. This is the actual significance and use of the ASTM standard. And as it says, the test method is designed to impart tensile impact energy to a butt-fused plastic pipe specimen. So it's perfectly adequate to use this test method on PVC. And key, though, is that you record the energy to fail the specimen. You plot the load over time curve of the test specimen, and the energy recorded at yield and rupture and the mode are used as criteria in the evaluation of the butt fusion joint. So this is a very good test method, ASTM test method, to determine the integrity of a butt fusion joint. You determine the integrity, and then you also want to, of course, again, compare it to the base material, as in any test method to evaluate butt fusion. This is a typical plot from the report using the ASTM high-speed tensile impact test. This is for the control 8-inch PVC pipe. This is a plot of the stress as a function of time in milliseconds. Remember, this is a high-speed tensile impact test. You can see there's a rapid rise and then a gradual decrease. The important thing to determine the integrity of the butt fusion, as stated by the ASTM test method, is this plot of stress versus time. The area under this curve is the energy. And the McElroy-McSnapper computer program actually calculates the energy for you. It does an integration of this area, and it calculates, and it actually plots the energy for you. And as you can see, in the case of the control pipe, the energy is about 750. This is a butt fusion made from that pipe. Now you can see that the stress is fairly high. So if you were to just compare the stress of the butt fusion to the stress of the control pipe, you'd say they're about the same. But if you look at the elongation, there's nothing. It's very brittle. There's no elongation. And if we look at the area under the curve to calculate the energy, it calculates it for you, and it's about 7. The energy to break for the PVC control pipe was 750 foot-pounds per square inch. The energy to break for the butt fusion was 7. That's about 9%. And that value, using this high-speed tensile impact by another laboratory, agrees very well with our values of between 5 to 10% for the standard tensile impact test that we did on the butt fusion joints. Well, what is the butt fusion experience, field experience? Again, there have been a number of field failures with a butt fused PVC occurring several different locations. Locally, we've got Des Moines, Iowa, Gutenberg, Iowa, Pittsfield, Illinois, Plymouth, Wisconsin, Evansville, Indiana. Again, a variety of sizes.
Are there joint failures? Is that what you're saying on this?
These are butt fusion failures, yes.
The butt fusion actually failed?
Yes. Now, some of these are reported to be properly made, and some were, and they failed I don't know. Some of these may have been in service. I think some were in service. Some were during the installation. But these are butt fusion failures.
The actual joint failed, not the pipe.
Right. Yes. This is a. I don't think I have any pictures of it, but I've seen them where it's there's actually a clean separation between the pipe and between the two pipes.
I'd like to see that report.
I'm trying to remember. I believe there's a performance pipe article on their website which shows the butt fusion failures. So if you go to the performance pipe website, you'll see it right on their website. Okay, so how do these field failures compare to the laboratory data? As far as polyethylene, all of the PE butt fusion specimens subjected to tensile and tensile impact testing exhibited significant ductile elongation, necking, and compared well with values for the control pipe. That's the key, is comparing the butt fusion to the control pipe. The polyethylene butt fusions conform to the melt bead requirement, and they all passed the bent strap test. These are very good laboratory results, and they compare very well with the butt fusion, very good butt fusion field experience for polyethylene. Like I said, it's been used over 50 years. It's used extensively in the natural gas distribution industry, where we have to have leak-free joints. In the case of PVC, all of the PVC butt fusion specimens subjected to tensile testing had a very low elongation to break, about 3% of the control pipe. In the tensile impact test, our testing showed about 5 to 10% of the energy to break compared to the control pipe, and that agreed well with the other laboratory high-speed tensile impact value of about 9%. The PVC butt fusion joints break at low levels of energy and low elongation. And I believe that's because it's showing that however these were made, there simply wasn't enough ductility to the butt fusions. These low laboratory values agree well with the field applications where there have been a number of butt fusion failures. So in conclusion, this is a summary of the laboratory testing that was done, the bent strap test, the elongation, tensile elongation of break, the tensile impact testing, and the high-speed tensile impact testing. In summary, butt fusion of PVC pipe is still relatively new. My own personal feeling is that I think butt fusion is a very good joining method, and I see no reason at all why butt fusion can't be used for PVC. I simply think we need to do a little bit more work on fine-tuning, honing in on the butt fusion process so that it does give good butt fusion joints. I think that's what we all want, is to have butt fusion joints with high integrity. As far as I'm aware, there are no published butt fusion procedures for PVC, and there's no industry-accepted test methods for qualifying PVC butt fusion joining procedures. It's still relatively new. And I think as far as the industry is concerned, that's what we need to do. We need to work together as an industry and come up with ASTM or AWWA guidelines for proper procedures and proper qualification methods for the butt fusion method. Even when properly made, PVC butt fusion joint integrity appears to be low compared to the pipe, and this has led to many field failures. I'm a consultant for plastic pipe. Plastic pipe in general. I have polyethylene clients, I have PVC clients, polyamide, cross-linked polyethylene. As a consultant, I don't want to see failures occur. It gives a bad name to plastics in general, gives a bad name to any material that fails. You're all probably, I'm sure, familiar with the polybutylene fiasco that we had in the water industry. So as a consultant, I want to see improvement in things that we're doing. So I want to see whatever we can do to make sure that we have good and properly working plastic piping systems. There's a lot of benefits to plastic pipe, and that's why plastic pipe is used in so many industrial applications. It's used worldwide in gas applications. Plastics are used in water applications, mining applications, now being used in the nuclear industry. There's a lot of applications where plastic pipe is used. The predominant material for plastic is PVC, There's about 10 billion pounds a year of plastic pipe that's used in the United States. 7 billion of that is PVC. It's the most popular material to use. About 2.5 billion is polyethylene. Those are by far the two most common types of plastic materials that are used in these applications. Why? Well, there's no corrosion. If you were here for the previous presentation, you saw all the corrosion that occurs in metal pipe, in cast iron, ductile iron, steel, etc. There's a lot of corrosion. Corrosion does not occur in plastic pipe. Plastic, polyethylene, PVC have very good, excellent long-term performance. Lower installed costs. They're easy to join. If the butt fusion is done properly, it will not leak. Plastics are easy to install. They're lighter weight. They're easier to handle. So there's a lot of advantages. There's a lot of reasons why PVC is used. There's a lot of reasons why polyethylene is used, and they should be used. Whether it is PVC or polyethylene, personally, as a consultant to plastic pipe, I believe the future is very bright for plastic pipe as a key piping material to replace our current failing metal piping infrastructure. Many of you, I'm sure, have seen the grades that have been given to our infrastructure for water, D, D minus, F, whatever it is. We have a failing water infrastructure. It needs to be repaired or it needs to be replaced. If it's going to be replaced, I strongly urge you to consider plastic pipe, PVC pipe, polyethylene, but I strongly urge you to consider plastic pipe. With the knowledge about rapid crack propagation that I talked about today and how to avoid these long-running cracks, with the knowledge about butt fusion guidelines and how to get good butt fusions, I believe that water design engineers can design their plastic water pipe systems to avoid these long-running cracks and have a safe, reliable, and cost-effective plastic piping system for their water piping needs. With that, I thank you very much, and I'll open it up to any questions.
Any questions for Gene?
Yes, sir.
Lifespan of pipe, what do you, plastic pipe's been out there for years now,
What's the expected lifespan? In the case of, let me give you two cases, PVC and polyethylene. PVC has a very ductile regression line. There's no change in slope. The expected lifespan for PVC that's properly installed would be years and years and years and years, hundreds of years. In the case of polyethylene, it depends on the type of polyethylene. The early generation polyethylenes had an early knee or ductile to brittle transition. So there were a number of failures in some early generation. I'm talking 50s, 60s, 70s. Polyethylene pipes that failed in a few years. If we're talking about today's materials, like PE 4710 I talked about, these materials have such high resistance to slow crack growth, they don't have a ductile brittle transition. They will not fail by slow crack growth. They are now, like PVC, they have a straight regression line. So the life expectancy of the new polyethylenes, PE 4710, the life expectancy of PVC that's properly installed, properly joined, would be hundreds of thousands of years.